So, for the last hour of today's session, we want to dive into about the various processes that we care about when we model aerosols in the atmosphere. And so this is going to probably be a shift for what you are used to when you are modeling aerosols in the combustion chamber, right? So the timescales are very different, the temperatures are very different, the pressures are very different. So we make different approximations and different assumptions. And so if something seems strange to you, just ask, right? Because we have to have this adjustment in conversation. Okay, so let's start with simplifying. So after telling you about the composition space, it's high-dimensional, and this is really what it is, and this is how we should think about, let's not worry about it for a little while, right? It makes things much easier to think about aerosols just in a one-dimensional space, just the size distribution for now. And this is a really good assumption when you only deal with one component. Let's say water droplets, or dust particles, or sea salt particles, or you get the idea, right? If we don't have to worry about heterogeneity in composition, if everything is just one species, or an internal mixture, as a matter of fact, right, then we just can express everything as the number distribution and figure out how does this evolve in time. And then once we are comfortable with this, we can generalize. And so then our aerosol state is actually the number concentration of particles, the little n of d, or what also is done for convenience reasons. Sometimes it's the number concentration of particles in a certain volume range, right? And so that's kind of like an equivalent way. Either it's little n of d or little n of v. And that is generally a function now that depends on time and location in the atmosphere. And yeah, that's it. And we need to formulate an equation for that number distribution. And so the processes that are acting on this number distribution, how we basically want to get to this, right? So what is this dN by dt of, let's use the v, t, and maybe also the position. And then what does the right-hand side look like of this equation? And as a starter, I want to focus on the birth. And then as a transformation process, we will focus on coagulation. So the gas particle partitioning we will do tomorrow. And then the removal, the dry deposition. Okay, so let's see how far we get today. And then we will come back to the rest tomorrow. Okay, so this, and then as a reminder, right, so the way we should think about this is, so we have our real world phenomena, so the aerosols that get emitted, transformed, and removed. The first thing we have to do is we have to cast this into an equation, right? And once we have that mathematical equation, we can think about how to discretize it into a numerical model, right? So these are two different steps, the mathematical formulation and then the casting it into a numerical model. So the mathematical formulation is this, and then the casting into a numerical model is, now I have to choose, am I choosing a modal model or a sectional model or a particle resolved model or bulk model, right? And depending on what I do, I have to do more work to get this equation into the right shape. But that is our governing equation. So we have our size distribution here, and then the different processes that are acting on it. And so I already labeled them. The first two are basically the transport, right, in the atmosphere. And the interesting thing is, each of these terms, there's a lot of physics that goes into these different coefficients, right? So the turbulent transport, for example, this K is the turbulent diffusion coefficient. So the turbulence people, that's what they need to figure out, right? And we need to use that to use this here. Then there is advection transport. So both of these together are the transport terms. Then the next two terms is when particles meet each other, right, and form a bigger particle. So we call this coagulation in aerosol science. And so there is a gain term and a loss term, and we will look at why they look like this in a second. Then there is an emission term, so we can emit particles into our in our grid box. And the next two are the chemistry terms, right? So there is evaporation, condensation of different chemical species, and water is a little bit of a special one, so we tend to separate this out, but the structure of the term is the same, right? And then there's another term right here called nucleation. So that's the new formation of particles from the gas phase. So that's pretty much what we are concerned with. And yeah, so let's jump in. And so just as a reminder, so this little n of V is the number concentration of particles in a certain volume, particle volume range, small volume range, similar to the n of D, which is a certain diameter range. Okay, so new particle formation in the atmosphere. It's this term right here that injects very, very small particles on the order of a few nanometers, right? So we're making really small particles. And so what happens is we have certain gas phase species in the atmosphere, and those species don't like to be in the gas phase, right? They form clusters. And the question is, are these clusters going to be stable or not stable? Can they survive? And then can they grow, right? And so if you really want to simulate this explicitly, you would have to employ molecular dynamics simulations. In these kind of chemical transport models or global models that I've been working with mainly, it's a highly parameterized process, right? So here is your first encounter with something that we have to represent because it's the source of new particles in a size range of very small particles, but we cannot represent it explicitly, so we have to parameterize it. And then the questions that people ask is, so okay, how does it actually work? Like, which chemical species are responsible for forming these new particles? The answer is it's primarily driven by sulfuric acid. Where does sulfuric acid come from? Do you have a rough framework of?
Burning coal.
Mm-hmm. Produces SO2, and then that reacts, and then you get sulfuric acid, exactly. But then, you know, these really, really tiny particles, as they are formed, they are way too small to form cloud droplets, right? So the next question then is, do they actually grow? How do they grow? What species are involved in the growth of these particles? And if you think about health impacts, right? So the ultrafine particles are, these really small particles are a big concern because those are the ones that can penetrate really deep into your lungs. And so if you have a lot of ultrafine particles, what's their source? Where did they come from new particle formation? Did they come from the gas phase forming these new particles? Or were they actually directly emitted? Because depending on what it is, the abatement strategies will be different, right? Okay. And the composition might also be very different. And depending on what the composition is, their health impacts will be different. Okay. And so here, what do we see here? So this is a typical example how people look at this kind of data. So imagine you have a monitor positioned, a sensor, like an instrument positioned somewhere out here or anywhere, and you're measuring size distributions with an SMPS, for example. So one of the things that you have to do, you have to be able to measure small sizes, right, in the first place. And so that could be like a measurement result. So here's actually time, just like here, 24 hours, right? And then in this upper plot here, on the y-axis is the diameter of the particles, and the color is the number concentration, right? The dn by d log dp. What we saw as size distributions before is just one size distribution after the next, and then you color them, and then you get like this time evolution, right? And so what we see here, initially, there was like a lot of particles in this size range. They are there, right? So there's a maximum. And then at some point, around late morning, maybe noon, we get, so here, down here are really small sizes, right? We're getting these new particles appear that are really, really small, right? So this is a nucleation event. And then they grow, right? Can you does this make sense that this is like a growth? Here they appear, and this is where they grow. Does this make sense to you? Okay. And so this is from now 2012, right? A while ago, right? And so people were wondering, okay, how does this work? Why does this happen around noon? So this is not just one time that this happened, right? This happens repeatedly. And so it goes together with the solar radiation. So that's the blue trace, right? So the solar radiation becomes more intense in the middle of the day. That's no surprise. And then also the sulfuric acid concentration also was rising. And then you can see when you form these new particles, it drops, right? Because you take some of the sulfuric acid to make particles. Yeah, and so that would be a typical signature of a new particle formation event in the atmosphere. Okay, so now how do we get this? What we need is like a nucleation rate, right? So when we model things, we always need rates to put in our prognostic equation. And so the CMAQ model, this is the model of the EPA, Community Multiscale Air Quality Model, I think what it stands for. It's a modal model, so it has 3 modes, and it's very sophisticated in terms of the chemical processes it actually considers. And the modeling team there works really hard to get good agreement with the various stations that they have all over the US. And they were looking into, okay, how do we do new particle formation properly, right? So the injection of new aerosol particles from the nucleation from the gas phase. And so you can see there are these different ways of parameterizing it. So the first one, this is quite an old one when we started looking into this, is called the binary sulfuric acid nucleation. And so here they parameterize this J, which is the nucleation rate. As a function of the sulfuric acid concentration. RH is relative humidity. And temperature. And so basically they fitted a function to that. The water vapor, it's really like a nucleation that involves sulfuric acid molecules and water vapor molecules together. They form the clusters and then form these stable new particles. Okay, so the next one is interesting. It's called an ion-mediated sulfuric acid nucleation. So it also has sulfuric acid, relative humidity, and temperature, but also some measure or some concentration of ions. So we always have ions in the atmosphere, right? Like that's a normal thing. And so they help stabilizing these very newly formed clusters, right? So that's a big concern about this. Like once forming a cluster is one thing, but it really has to be stabilized to stay together. And when they are so small, they kind of tend to break apart. So the ions really help to stabilize this. Then later on, ions, okay, but then they also said, okay, there are these organic molecules, and they call them HOMs, highly oxygenated molecules, that help as well, right? So you form your initial cluster, and then these highly oxygenated molecules help to stabilize it further. And so there are a few different variants now, and you can see it's a very empirical way, right? You see these coefficients, it's kind of like this fit, and different people put forward different ways of capturing this process. It's all still the same process. And so then my colleague Ben Murphy from the EPA worked on, okay, what happens if we now implement? So this is one of these examples. You have these different expressions, and you're wondering, what happens when I implement this into a model? Is this actually going to make a difference? And so what they did is they have these different variants, and so this is California. They did this for California, and depending on which of these different equations you use to parameterize this one term, you get different results, right? So this is the color is the new particle formation rate, and depending on the conditions, right? If you have HOMs or not, like if you don't have any of these oxygenated molecules, then this won't be important, right? But depending on where you are in your modeling domain, it makes a bigger or less big impact. And so, if you ask me, so the binary sulfuric acid nucleation, this is the first one that we put into our models, and that's probably accounting for most of it. But depending on where you are, these different other mechanisms might be important. And at the end of the day, it's kind of like a superposition of all of them, and maybe even more, right? So there was also ammonia is helping, and amines, and so yeah, it just shows you the complexity, right? When you pick one of the processes, it's just one term in this equation, and suddenly this is a whole career that you can spend on trying to figure things out and measuring things and implementing it into models, and yeah, so there's that. So still many open questions about how new particle formation works, and how we can put them into models. Emissions is also like a huge area. And so for us, for the US, we are in the fortunate situation. There are actually really good, comparatively good emission inventories available. So the EPA produces them, right? So the Environmental Protection Agency produces them. And they are produced for total annual emissions for a source. So you have your different sources. Wildfires is very important. And then, all our activities, they try to estimate how much aerosols are they emitting on a yearly basis. But of course, for our models, that's not enough, right? We don't just need it on a yearly basis. We need to have it on a gridded basis. We need it hourly. We need it for different seasons. So there's from this yearly emission rate that the NEI is giving us, there's a whole nother model, an emission modeling process that eventually gives us the emissions that we actually ingest in our chemical transport models. So the emission inventory reports pollutants such as CO, carbon monoxide, NOx, VOC, volatile organic compounds, SO2, and PM10. But that's not enough for us, right? That's not specific enough. It's aggregated over the whole year. It's per county. So what we need to do, or somebody needs to do, is to speciate the emissions into what we actually treat in our model. So we don't just have NOx. We need to know NO and NO2, right? We need to know the different organic compounds. We have model species for those. We need the PMs. We need them speciated, not just PM10, right? We need to know what is organic carbon, how much BC, how much SO4, and so on. We need to allocate it spatially. So per county is not enough because our grid boxes in these chemical transport models, like for example CMAQ, right, from the EPA, actually has several grid boxes in the different counties. So we need to apportion this, and this goes often by population density, right? And then also like a diurnal profile and seasonal profile. So there's a lot of processing and massaging the data until we actually can put it in here, right? So it's a whole research area and people's careers in just this one step. Okay, so that's the birth. So basically, remember 2 ways from the gas phase. Sulfuric acid is the key player, but other types of chemicals, gas phase species are involved as well, or particles are directly emitted. Oh, what I didn't mention is, so these are the anthropogenic emissions. There are other primary emissions, I should put this here, plus natural emissions of dust, mineral dust, so, you have areas in the US, for example, in the Southwest, where you have dust being emitted into the atmosphere, or, even like, when the fields get really dry in the Midwest, so there is dust being emitted there too, so you want to capture that. And then sea salt aerosol. And they don't come from these NEI emission data. They come from parameterizations that depend on wind speed. So you need to have a good meteorological model to know what's going to happen there. And in terms of dust, you also need to know something about the soil moisture, right? So as the soil is drying out, the dust becomes much more readily being stirred up by the wind, and when it rains, more or less. So so it's all a coupled system with lots of moving parts here. Okay, ready to go for the next one? The next thing is coagulation. All right. So definition of coagulation. So if aerosols move around, and if they move with different velocities, they may collide and stick together, right? And so the reasons for having different velocities, there can be several reasons. The main reason for aerosols is Brownian motion. So do you know what Brownian motion is? What's Brownian motion?
The individual molecules hitting the finite-sized particles.
Yeah, exactly. So the aerosol is being bombarded by the gas molecules around it, right? And it responds to this more or less sluggish. The small particles respond to it very readily, so they move quickly. And the heavier particles, they don't move as quickly. So that introduces relative velocities because of that mechanism, and then sometimes they bump together. Okay, and so that coagulation, just as a reminder from our big equation, is these 2 terms. And the key here of course, we need the size distribution, right? So that's our N. But we also need this K. And so K is the coagulation kernel. The probability of coagulation is quantified by this K coefficient. And depending on what the mechanism is, this will take a different form, right? Okay, and so here in my favorite book, Seinfeld and Panga's Atmospheric Chemistry and Physics, that's just the title, very simple. They have this figure here, so the size of one particle on the x-axis. And the other, so particle 2 has variable size here, and particle 1 is always 1 micrometer, right? And so then this K, you need to know the 2, because it's an interaction, right? So you need to know the 2 sizes of the particles involved. And so let's look at Brownian motion, right? So if one particle is 1 micrometer and the other particle is variable from 0.1 to 10, Brownian motion causes a coagulation kernel, or you can think of the probability of colliding that looks like this. It has a minimum for when the particles are similar size, and as they get more disparate in size, the probability goes up. Does this make sense to you, that it has to be like that? So if you have the collision probability is enhanced if they are different sizes, right? Because the small ones, they move around like crazy, and the big ones just sit there. So it's very likely that they collide, as opposed to when they all move at about the same speed. It's just not as likely. And so there are a couple of other mechanisms that can cause relative velocities. Gravitational settling, this becomes really important for the rain formation, right? The cloud droplet settling. How to make rain droplets out of smaller cloud droplets. Not so important for aerosols. Why not? Because they are just not settling as quickly, right? So it's just not that relevant. And then shear flows and turbulent flows can also cause relative velocities. Not as important in the aerosol world, again, because with the turbulent flow, we assume, and it's a pretty good assumption, somebody was asking this actually, that they don't have much inertia, right? So they just follow the eddies, and they all follow in the same way, so there's not much preferential concentration, which you get for Stokes numbers that are not equal to 1 anymore. So less important here. Again, more important for clouds. So for aerosols, Brownian motion is really key. That we want to incorporate that. So let's do this. Yeah, so Brownian motion, random motion of particles that are suspended in a fluid, which could be liquid or gas, so an aerosol, right? Resulting from their collision with the fast-moving molecules in the fluid. And so then they do this random walk, right? And so so these are paths. So I started, this is actually a little simulation, what that looks like. So we start at position 0, right here. And then we let this is a path then from 3 different particles, right? And so that's how they move around. And when you plot their final after some certain time, if you look how far they got away from the origin, you can see it's kind of like normally distributed. And then the intensity, right? If you take the square of the displacement, it's this distribution, and so on. And so there are really good theoretical frameworks to deal with this. Okay. So now we need to do a little excursion here, and I have some notes. So are you familiar with these different regimes, how a particle perceives the surrounding gas? Do you know all about free molecular regime and continuum regime? For sometimes, like chemical engineers, I think they all know this, and then atmospheric scientists, they don't. So, so let me just review this real quick. So, and it's kind of like tricky, right? Because yeah, so basically this is the issue, how a particle perceives the surrounding gas. And depending on what it is, we need to, our K expression will look different, right? And so that's, I think it's in general easy to understand. If a particle is really big compared to the mean free path of the gas, it perceives the gas as a continuum, right? And as the particle gets smaller and smaller, more on the order of the, so this would be, so A would be the continuum case. In case B, the particle is so small, it's on the order of the mean free path, or maybe even smaller, actually, in this sketch. So that's a different regime, right? It's the free molecular or the kinetic regime. And then there is, of course, the in-between regime. And the dimensionless number that quantifies this is the Knudsen number. It's the free mean path of the surrounding air molecules divided by the radius, or you take 2 times lambda divided by dp. And so now my question for you is, what's the free mean path of the air molecules at the surface, like order of magnitude? Because that will determine what we need to use, right? What kind of expression we need to use for our. Is it more than 1 micrometer or less than 1 micrometer? Free mean path. So the length that it takes for the air molecules to collide with each other, right? More than 1 micron? Less? Less. Less than 0.1 micron? Yeah, right? Yeah, it is, let me tell you, 0.0651. At 298 Kelvin and 1 atmosphere, this is the mean free path of the air molecules. And so our regimes are, if a particle is much larger than 1 micron, we can apply the continuum regime approximations. If it's smaller than 0.01 micron, we can apply the kinetic regime approximations or expressions. And in between, we have, I don't know what we're going to do. So that's tricky, right? So remember the size distribution of aerosols? Where are they? Is it this, or where are we? Everywhere, yes. That's the key, and that makes our life not simpler, right? So we have to be ready for this. So a lot of stuff is actually happening in the transition regime. So we have to deal with that. Sometimes we can make approximations and choose one or the other, but most of the time not. Another thing to consider, not all of the atmosphere is at room temperature, right? I showed you the vertical profile of temperature, it changes, and of course pressure changes too. And so the mean free path here is a nice graph of how we often plot things like, if it's a vertical profile, we put altitude on the y-axis in atmospheric sciences. And then the thing that we are interested in is on the x-axis. So the mean free path from surface level up to throughout the troposphere into the stratosphere increases, right, as the pressure decreases. So our regime, the Knudsen number, changes as well. Okay, so there's that. Now here is our expression for the coagulation kernel that people use in my field. And the first part, this part, is what you actually can derive for the continuum regime, and I will talk about these, what these variables mean in a second. And the second part here is a correction to make it work for the transition regime so that we can apply it for all particles no matter what size, right? So the first part here is applies for the continuous regime. Continuum, I should say. And the second part is a correction factor. And so that's quite a well-known, famous form of the Brownian coagulation kernel called the Fuchs form. Okay, so let's just quickly go through the different things here. The important thing, so the problem here is a D capital D is a very overloaded letter in our field. So for one thing, it's the diameter, right? And so here in this notation from our textbook, it's dp. dp is always the diameter of our particles. And then there's another d, it's d1 or d2. And so that is the Brownian diffusivities. And the Brownian diffusivities are derived by the Stokes-Einstein relation. And so for example, D1 is kT over 3 pi mu dP1, right? So the bigger the particle is, the lower is the diffusivity. The higher the temperature is, the higher is the diffusivity. And then we also have the viscosity in there. Mu is viscosity. And T is temperature, right? You probably know, everyone knows that. What else do we have? Yeah, so the C is the velocity of this is here the correction factor of the velocities, and the free pass, free pass, the L. And then G is just another, agglomerate all these constants and diameters to just a short expression for a lengthy term. And then, so here is our, okay, so that's another thing. These diffusivities here, there's actually also the C, this is another correction factor. C is the Cunningham correction factor. That's also correcting for kinetic effects. So, the point, I'm not expecting you to memorize these equations or anything, but in the simple K, there's a lot of physics that is kind of like embedded here, right? And then, so that's the classical Brownian coagulation coefficient that we use. There are actually interparticle forces that may modify this expression. So if you have charges on your aerosol particles, this may accelerate or intensify the coagulation or slow it down. Van der Waals forces are another possibility, or hydrodynamic forces between the approaching particles that could also be a modification. But typically, we don't worry about these, right? And there are studies that try to justify this. Most of the time, actually, we are fine with just using the Brownian coagulation kernel as it's written here. And that's what it looks like. So let's see here. It's a bigger. So how does this figure work? So again, because it's an interaction term, right, we have two diameters here. So one is on the x-axis from 10 to the minus 3 to 10 micrometer, our usual range. And then the other diameter are these different lines, right? And so you see what we already said. If the two particles have the same diameter, the coagulation kernel is actually lowest, right? And we could derive expressions for this that it increases here, and actually it becomes a constant as you go to larger values. So there are good reasons for that. But you also see if we stay down here at the small sizes, right, and we increase the sizes of the partner, the coagulation coefficient really, really increases. And so coagulation between a 10 micrometer particle and a 0.01 micrometer particle is really, really likely, right? So they coagulate. The big one sweeps up the small ones like crazy. And so if you think about these freshly nucleated particles that we just talked about from sulfuric acid, water, binary nucleation, and you have other bigger aerosol particles around in the atmosphere, will this freshly nucleated particle grow to become a CCN for a cloud droplet? Maybe, but it's also very likely it's just going to be swept up by one of these bigger particles and it's gone, right? So the survival time of these freshly nucleated particles in the atmosphere depend on the abundance of bigger particles. So that's why you need to have the whole size distribution represented. Okay, so this was Brownian coagulation kernel. All right. Did you have a question? Ah, okay.
Like this was for a fixed temperature, like a temperature 25 degrees Celsius. Is the behavior like observed similarly for like different temperatures? Does it collapse or like what would be the order? Because I'm presuming it must be very sensitive to temperature.
It is sensitive for temperature. So temperature is right in there. It comes in through the diffusivity, right? So the diffusivity is proportional to temperature. So we need to know the temperature of our region. Where are you? Here. Okay. And that definitely feeds in. Yeah. So you want to have the temperature to what the temperature actually is. Yeah. Okay. So that was a big story about this one coefficient in our governing equation right here. But the next thing I actually wanted to do, and so now we have 15 minutes left, is to tell you or to justify why these two terms look the way they look, right? So we said this is this coagulation gain and this is a coagulation loss. Well, what does this mean? I think that there is a gain and loss is easy to understand. So because this equation here tells you the number concentration for a certain size, right? Remember that? Number concentration for particles of volume, in volume V and V plus dV, right? And so now, if you have a certain amount of particles in that size range and you have coagulation, if a particle of that size range coagulates with any other particle of any other size, it's not going to be in that size range anymore, right? It moves to another size range. So that's the loss. That's the coagulation loss. And then conversely, if two smaller particles collide, and it's just so that they become a particle of that size or volume V, that's a gain, right? Two particles combine to form a bigger one, and if it's in that size, it will be counted as two losses in the other size ranges and one gain in that size range that we are looking at. So in other words, these two terms are just like a big accounting exercise, right? Like counting who goes away from that bin by coagulating with anything else, or being formed in that size bin from coagulation of two smaller bins. So, and the equation that does this for us has a name. It's called Smolakowski equation, or sometimes called population balance equation. And one typically derives this first as a discrete version, and then says, okay, now let's make the volumes, let's do the delta V, let's have it go towards 0, and then it becomes the continuous integrals rather than summation. Have you had this before? Have you looked at population balance equations before? I see frowning, and so let's do it, and then we are ready for lunch, okay? Okay. blank page. So population balance equation. So this is motivated by the question, how does a polydispersed population evolve? More than one size. Or if you start out with a monodisperse, everyone has the same size, and you let them coagulate, they become a polydispersed population, right? Okay, so let's introduce this variable, nk of t. It's a number concentration. Of particles with K monomers. So what's a monomer? A monomer is basically a molecule of a species, like a building block, right, of a species that this particle is composed of. Yeah, so that's what a monomer is. And then we can write down the formation rate of particles of that size. It's essentially the size of the particles, right? Formation rate, our rates are always J, so formation rate of size K is when two particles collide, and to make a size K, we have to combine K minus J and J, right? And then times N of K minus J, which depends on T, times N of J. And then we have to sum from J to K minus 1, right? So we combine, for example, to make a size 3, I think I have an example. That's what I want to do. Yeah, let's write this down. Example, size 3. Formation rate of the size 3 particles is, if I do the sum, it's K21, N2, N1 plus K12, N1, N2. And the coagulation kernel is symmetric, actually. So we can say this, so K12 equals K21. So this is 2, K12, N1, N2. All right, are you happy with that?
The n sub j, that's also an n sub j of time.
Yes.
Okay.
Yeah, they all depend on time. Thank you. What about the J expression? Is that how you would count this? It's double counted, right? So we have to multiply by a factor of 1/2. So this expression counts collision twice. So we need a factor of 1/2, and then the sum. It's difficult to talk and write these indices. I probably, if you see something off, just tell me. N of J of T, yes. All right, so, and if you look closely, I'm going to go back to our, see, there was this factor of 1/2, and that's Y. Now we know why. All right, and then this was the formation rate, and then we also have the depletion rate. So J depletion of K, and so that is, if N of K, if that size collides with any other ones, so this goes from 1 to infinity, then it's gone, right? And we don't need a factor of half here because we are removing two particles, right? So it cancels out each other. And so then we can put them together into our balance equation. Is the production or the formation minus the loss. So 1/2 times the first one, K minus J and J. So how do I combine particles to get exactly that size K? And then I can subtract the loss term. Like this. Okay, and so now, are you still writing? So this was the discrete version where we actually have discrete little K-mers, right? K monomers, things containing many monomers. So we can do this counting, but in practice, each aerosol has so many monomers. We are not dealing with 1, 2, 3, or 10, right? It's like thousands or millions. So that's when we go from these discrete sums to the integrals and to the continuous size distribution. So n of K becomes the little n of V, and the integrals summation becomes an integral. And this shows that I'm not a new particle formation person, because in that field, because they deal with these small clusters, they actually do that like this, right? They will have population balance equations that look at the discrete K-mer formation and destruction. But once you look at grown-up aerosols, you don't do this, right? We use the distribution function. All right. Good job, everyone, for hanging in there. Oh, before we disperse, so to speak, let's do this at the end, right? Discuss with your neighbor. If you want to understand, when is coagulation important, right? If you want to understand the variability of ultrafine particles next to a busy road, right? Because maybe you want to build something there, like some housing, and you're worried about the air pollution impacts and what's the number concentration, you want to model this. Or if you want to look at the seasonal cycle of aerosol mass concentration somewhere over the ocean, do you think coagulation is a relevant process for any of these? Or do you think it can be neglected? So let's take 2 minutes to discuss and then bring it together, and then we can go for lunch.
Yes, makes sense. I think also it's really important to keep in mind, like
word mass concentration,
all the particles that you have next to our boat.
I'm sort of not thinking in the
Like
dynamic debate
recently emitted by the ice or car or whatever, maybe in the middle of the ocean. Like maybe if they agglomerate in a few seconds, it's very old, but maybe the ocean is already
See, coagulation is not a relevant process. Coagulation is not relevant in the first phase, right? Because this is like a nanoparticle that is
Literally carbon.
I think it's probably important for both, like maybe
seasonal cycle
that you're interested in.
It also
Depends on the life cycle. Even before cooking, and what about before dying out? So this is about combustion.
Literally formation of clouds.
you have lots of small ones.
Well, basically cloud formation over the ocean because of like everything. So
The formation of clouds.
you can't neglect that. So like
Definitely for the first one, yeah.
So it would be nice
What about the second one?
you can't neglect in either cases.
time after like they like enumerate
Yeah, somewhere over the ocean.
like relatively fast. It takes like several minutes. Also compared with their residence time.
I think you can't
Maybe
neglect
they
in
need
either
it once like settled in a matter of like seconds.
Right, if
Like
you
it
are
all-
concerned with mass, yeah, because coagulation is really important for
I think it's important because again like ultrafine particles.
I think it might be more important for number one.
what do you guys think? Wrong. We have to do everything again.
Really?
Yes. Okay, to release you into the lunch break, I hear very varied opinions here. What do you guys think? With the busy road and the ultrafine many particles and coagulation. It's important. Why?
Most of these ultrafine particles, I'm presuming, are like small carbon particles which like sort of grow in size later on to become like I'm presuming something like a dust or something which has like finite size. And so coagulation is definitely important. Please.
So, but the main point is, remember, like, yeah, so you have lots of ultrafine particles that are emitted from your combustion engine, right? And so then what happens to them, right? So they coagulate like crazy with pre-existing ones. And so that will reduce actually their number concentration. And you probably want to know, depending on how many bigger coagulation partners you have, how quickly is that decline, right? For example, as you go further away from the road. So the coagulation coefficient for these small ones is really high, right? That was one of the figures. So that's why we need to care about them. Number concentration will change very rapidly. Also, another thing I didn't point out, but the coagulation rate, it goes quadratic with number concentration, right? And if you have a high number concentration, which we said, I didn't actually say high number concentration, but yeah, it's implied, right? So then you have high coagulation rates. Okay, so what about the remote ocean and the mass concentrations? If you are concerned about mass concentrations. Right, exactly, because it's actually mass conserved, right? You combine two particles, you change the number, but the mass of the total doesn't change. And if you're just interested in climatological behavior of how much mass concentrations you have, coagulation is not that important, right? Yeah, that's it. All right, thank you all. And we'll see you